In that case, oh, Anna's just made it. All right. Yeah, we can get started. So, hello everyone. Welcome to the One World Combinatorics Onwards seminar. Our speaker today is Josef Rukavicka. He is going to speak to us about palindromic length of infinite aperiodic words.
Hello, all together. Thank you for the introduction. I'm glad to have the possibility to present my new result in this conference. Yeah, the name is about the palindromic lengths of infinite aperiodic words. Above on the page, you can see the link to the preprint. You can see this. I have published the preprint in the October, so it's a really quite new result. And currently it is submitted and under the review. So probably there will be in the future some new versions of this paper with some improvements based on the comments of the reviewers. But for the moment, you can use this first version. I will start as usual with a couple of definitions. For those of you who don't know palindromic lengths, of course, palindromic lengths of infinite words is not defined, so the name of the paper can be a bit misleading, but I will clarify this on the next slides. So let us start. Yeah, I consider some finite alphabet of symbols. Then I define a finite word of length n. It's a sequence of the symbols or of the letters from the alphabet. It's clear I consider also an infinite word, which is an infinite sequence of the letters. And I count the letters from the number 1, not from 0. Then, yeah, the crucial object or the crucial notion of the paper is the palindrome. I guess you know what palindrome is. Here is the formal definition. Here are also 2 examples. So these are the sequences that can be read from left and from the right, and they give the same. So this is the palindrome. Palindromic lengths of the finite word V is equal to the minimal number of palindromes whose concatenation is equal to V. This is the definition of the palindromic lengths. So it is explicitly defined. We consider only finite words. For the infinite word, yeah, I think there is no definition for infinite word. Here's some example. For example, for the word 001001, the palindromic length is 2. You can easily see that we can split it into 2 palindromes, and not less. The word itself is not palindrome, so it cannot be 1, but it is 2. And you can also see that there are 2 possible options how to split this word into 2 palindromes. So palindromic length is unique, but the factorization into the palindromes is not unique in general. And then in 2013, the following conjecture has been presented. If X is an infinite word and key is an integer, okay, sorry, the function PL is the palindromic length of the word in the brackets of the word U. I didn't state the definition. So again, if X is an infinite word and key is an integer such that the palindromic length of all factors, of all finite factors of the infinite word x is lower or equal to the key, then the infinite word x is ultimately periodic. So it means that the infinite word x has some prefix that we can cut off, and the rest, the infinite suffix, is a periodic word. So this is the conjecture. It has been presented in this paper on palindromic factorization of words. I would say this conjecture attracted quite a lot of attraction. You can see there are quite a number of papers that try to solve this conjecture. For the moment, there were only partial solutions, and also some properties of the palindromic lengths have been presented, including my 2 papers I published already in the past, 2 papers dealing with palindromic lengths. I presented some new properties of the palindromic lengths. Of course, I tried to solve this conjecture, but I failed at the time. But now, in the last year, I found a solution that I will. Yeah, this is actually this is the result of my paper that I present. I solved this conjecture positively. Yeah, it means I confirm that the conjecture is true. Okay, I will come to the proof. I think the proof is not too technical. Yeah, I think I had some other papers, other results that are much more technical and much more difficult to read. In this paper, there are some concepts, some ideas that can be easily presented and understood. I will start with the most essential one. For the moment, we can forget the palindromic lengths. We can forget the other results. I will just present one simple but essential result for the paper. For this, I need only a couple of simple definitions. The first is I define the minimal period of the word t. I think minimal period is nothing new. And then I define the order of the finite word t as the length of the word divided by the minimal period. Yeah, this is not a new concept. I already seen this definition of order in some other papers or textbooks, but yeah, I think maybe you know, maybe not, but it's a simple definition. So the order is practically the number of the repetitions of the minimal period in the given word. Important here is that it is not an integer in general. It is a rational number. Then I define that a palindrome is non-periodic if the order of the palindrome is lower, strictly lower than 2. This definition, as it is presented in this way, is new. I've never seen this definition. This is my invention, but I think there is nothing complicated about it. Then for the given word, I define the set NPP. It is the set of non-periodic palindromic prefixes of the word T. Non-empty periodic palindromic prefixes. The set is, of course, always non-empty. At least there is the first letter of the word T, because the letter is palindrome. So this is this set of this non-periodic palindromic prefixes. And then I define that I call the word T ordinary if for every factor of the word T we have that this equation holds. It means that the number of the non-periodic palindromic prefixes of the word T is bigger or equal to the number of non-periodic palindromic prefixes of any factor of the word T. So this is all what I need for the essential result. I think even the ordinarity is not necessary, but I put it here. So now I consider a finite word Z such that the number of the non-periodic palindromic prefixes of the word Z is equal to H. Here I say that the factor is ordinary. For the paper, for the whole result that proves the conjecture, it is necessary, but only for the essential result, for the essential part of it, for the result that I will now present, this is not necessary. So this is why I put it in the brackets. Okay, now I define the non-periodic palindromic prefixes of the word Z. I note it as Z1, Z2 till ZH. So these palindromic prefixes are the set NPP. Also, I defined that the word Z is palindrome itself, and then it is equal to the, and this is, yeah, that it is a non-periodic palindrome, and then I can say that Z is equal to ZH. And then I defined that the Z1 is shorter than Z2 and so on. So the palindromic prefixes are ordered based on their lengths. It is also clear, as I said, that the Z1 is the first letter of the word C. So this is what I consider, and then I define the Z1, Z2, and so on with head. And I said, and this is this definition, if I concatenate Zi and Zi with head and Zi, then this concatenation is equal to the Zi plus 1. In the paper, I show that this Zi with the head is defined and is non-empty. For the moment, it may not be obvious, but it can be easily proven because of the non-periodicity. Since the order is strictly smaller than 2, this is easily to be proven. So the definition as it is here is okay. There. I hope this is, yeah, this is clear. Now for this word Z, I define the so-called base positions. Here is the formal definition. Well, it can be a bit confusing. I will show you some picture. I created a picture for this presentation, which is not in the paper. I will include it in the next versions. Probably, I think it will help. Okay, here's the picture. I have the factor Z, and these half circles that you can see are the palindromes Z1, Z2, Z3, and so on. For the picture, I consider that H is equal to 4. And since the crucial observation here is that the prefix of a palindrome is also a suffix. So for every palindromic prefix of the word Z, for example, of the word ZI, I have that the palindromic prefix is also a suffix of the ZI. So finally, I have this structure of palindromes with all the occurrences of, not all, but with these occurrences of Z1, Z2 till Z4. There may be some other occurrences, but I'm not interested in them. I'm interested only in these, let's say, natural or canonical occurrences of these palindromes. And now I defined the starting positions of the smallest of the shortest palindromic prefix of the Z1 of the letter. These are the base positions. So for this case, I have 8 base positions. I hope, yeah, it is. I think it is clear. Yeah, you can notice that the number of the base positions grows exponentially with the age, with the number of the palindromic prefixes. So except to the last one with the age, so it is 2 powered to IH minus 1. So this is the definition of base positions. If you look back on the definition, this is the set B with the tilde over. The set B is the set of pairs of integers. The second integer in every pair, in every couple, is the position. The first integer in the couple is the index of the palindromic prefix Z. So it is 1, 2 till H. So the set B are the couples of these integers, where the first one is the, let's say, in the size of the palindromic prefix, and the second one is the position of it. Yeah, the definition, maybe you can need some time to understand the definition, but from the picture, I think there is no doubt. So I continue. Now I define in the paper, I often use some interval of integers. So for it, I define this notion n with 2 parameters, and this is the set of all integers between these 2 parameters. I use it many times, so this simplified the paper a bit. So I define it, and now I define the set UC. Okay, I will try to explain what it is. The set UC is the set of sets of positions. So if some element is from the set UC, it is a set of positions from the word Z. And not every set. The set has the following special properties. If I consider some factor of the word Z, which is defined by the starting and the end position, in this case, I use the notation me1 and me2. This is the starting and the end position of the factor that I consider. And if this factor has a period, if this factor is periodic with the period xi, this is the second line of the definition, then I require that there is a set E, also the set of position, the set E, such that the set E, that the size of the set E is smaller than some given constant. In the paper, it is the constant 8, but it is smaller than the constant. And the important thing is that the intersection that how do you say? If I make the intersection of the positions from the set S with the factor, then this intersection is equal to the intersection of the set S with the 8 periods with the C2 periods given by the set E. It means maybe once again, so if I take the bounded number of the positions from the set E, and if I consider the factors for every position, I consider the factor starting in this position and ending in the position with the starting position plus the period Xi, then I claim that the intersection is the same. Yeah, so I think if it is the last line of the definition, maybe the definition was a bit confusing, the explaining was a bit confusing, but as it is stated, I think it is clear. So the important thing is, if I have the important message is, if I have some factor which has many periods, then for the intersection with the set S, only small number of periods are important. I can consider only this small number of periods if I am interested in the intersection with the set S. All the other periods have no intersection, or the intersection of these periods with the set S is empty. So this is the definition of the set UC. I think the abbreviation, by the way, UC stand for uncovered or uncoverable. I don't remember exactly what I meant with this, but it was something like this. And now come the crucial result. This is the essential result of the paper. On the next slide, on the next 2 slides, I will show you the proof. The proof is surprisingly simple, and the proof is really important. So what it says, I will now explain what's the meaning of this proposition, why it is so important. In the paper where the conjecture was stated, in the paper from the 2013, in the paper it was also, the conjecture has been proved for the infinite words that are alpha power 3, meaning if there is some integer alpha such that the infinite word is alpha power 3, then the conjecture has been proved. In the proof was like that due to this alpha power 3ness, it was possible to consider some bound on the number of palindromic prefixes on every position for some given factor. There was this alpha power 3ness allowed the authors to derive some upper bound on the number of palindromic prefixes, and then using this bound, it was shown that using the concatenation of at most key palindromes, I can reach only a small number of positions. Now, for some properly selected factor, the number of positions that could be reached by concatenation of at most key palindromes was really small. Yeah, this was the proof. My proof is a kind of generalization. I do not consider all the positions of the factor. I consider only base positions. And due to this proposition, due to this result, I can show that I cannot reach all the base positions using only key palindromes in the concatenation. Because this result says practically that no matter how many repetitions of the period I have, the factor can be arbitrarily, can have arbitrarily many periods, then for the intersection with the base positions, only a small number of them is relevant. So when I prove this, that the base positions are from this set UC, I basically say that I don't care about many periods. For me, only a small number of periods of every factor is important. So yeah, I think for those of you who already tried to solve this conjecture, maybe you have the feeling that this is a really essential observation. For me, for example, as I discovered this, I knew it was a game changer, so to say. So, and surprisingly also, it's really easy to be proved. So in the paper, it takes only a small piece of the paper, small part of the paper. The rest of the paper is dealing with something else. I will explain it later. So now to the proof of this result. For this result, I need one more definition. I need the definition of the height, which is on the fourth line here. Maybe I will explain it using a picture. Yeah, I think it will be more simple. So I prepared one more picture, or there will be another, but for this proof. So I have again the word Z that I had, and now with the blue rectangle, the blue rectangle represents a vector of our choice. It can be arbitrarily chosen. And for this given vector, the height of the vector that I defined on the previous slide here, it is basically the red half circle. It is the 2. It is the red half circle is Z2. It is the palindromic prefix Z2 because it is the biggest one, which is whole in the vector. This is the definition of the height. The biggest whole palindromic prefix, which is in the vector, defines the height of the vector. So in this case, it is 2. Yeah. And now, when I have the definition of the height, I can make the following observation. In any vector, there may be at most 2 whole occurrences of this biggest half circle. Because on the picture, if you consider, for example, the vector, the palindromic prefix Z1, there are 3 whole occurrences in the blue rectangle. And this implies that there is also one palindromic prefix which is bigger than Z1, and it is this Z2. So as soon as I have more than 3 whole occurrences of any of these palindromic prefixes, it implies there is also one whole occurrences of some bigger palindrome. This is easily to be seen. In the paper, it is described and explained. Here, I think the picture makes it clear. Because the palindromes, you can notice they have some structure like a binary tree. So, and if you consider these palindromes like inner nodes of the binary tree, then you have that for 3 consecutive inner nodes on the same height, on the same level. There is also inner nodes which is higher in the binary tree. Yeah, so and that's it. So it means I can have at most 2 whole occurrences of the biggest vector. Also, I can have there 2 partial occurrences of them, namely at the beginning and at the end of the vector. There may be some cut, like in this example, there is a cut of the Z2 at the end, at the beginning not. So there may be 2 partial occurrences. So it means 2 whole occurrences and 2 partial occurrences. This says there are at most 4 occurrences of the biggest palindromic prefix, Zi. And since every palindromic prefix, Zi, is by definition non-periodic, means the order was strictly smaller than 2, it implies that in every one of them, there may be at most 2 periods of the vector, of the blue rectangle. If the blue rectangle is periodic, it may be that it may have many periods, but in one occurrence of the palindromic prefix Z, I, there may be at most 2 periods. And if I have 4 occurrences at most, it means that there are at most 8 periods of the blue rectangle that have some overlap with the base positions. So this is basically the proof. So once again, no matter how many periods I have, the blue rectangle can have arbitrarily many periods. Only 8 of them are important for us when we are dealing with the intersection with base positions. Only at most 8 of them contain base positions. And this is the most essential result, most essential observation of the paper. The rest, I don't want to say that it is straightforward. There is still a lot of cases that must be carefully considered, but yeah, this is the essence. I would say if you know this result, you would be able to solve the conjecture yourself, given enough time, of course, because I think with this result, the direction of the proof is given. Okay, so now I will continue with the rest of the paper. As I said, this result takes 2 or 3 pages. The rest, for the rest, I will need quite many definitions. I will not show all of them. Yeah, I will try to keep it simple. We will see. So first thing that can make it, let's say, a bit complicated to understand is my usage of the special letter B. I define some special letter in the given alphabet that I state as B, and I use it for padding. The given infinite word that I have, I transform it into another infinite word in such a way that on every second position I have this letter B. It is more or less obvious that for the conjecture this has no influence. If the conjecture holds for the first word, it holds also for the padded word. I think, yeah, but there are some. It has some technical advantages and some proofs. I think for this presentation you can forget about it, but just you have heard from me there is this special letter used for padding. Yeah, here is just explanation for the padding. It says that every second letter is the B. It is the, in this definition, it is the odd. These are the odd positions. On the even positions, there are the original letters from the word X. Then I define the, yeah, this is still for the definition of the padding. Yeah, as I said, every second letter is the letter B. Then I define the padded palindromic lengths. It is defined as it is explained in this definition. It is defined only for the words that are not starting with the letter B. Yeah, also I claim that the letter B does not occur in the original infinite word X. So for the factors of the padded word such that they don't start with the letter B, I defined the padded palindromic lengths as it is described here. Okay, and it does not end with the letter B. Yeah, then I define for the infinite word, I define the maximal palindromic length and the maximal padded palindromic lengths as it is defined here. It is just over all the finite factors, I select the one with the maximal with the maximal palindromic length or the padded palindromic length. And I show, yeah, as I said, for the conjecture, there is no influence. If the finite factors of the original infinite word are finite, then also the padded palindromic length is finite. So to prove the conjecture, I can consider this padded palindromic length of the padded infinite aperiodic word. Okay, now, yeah, this is some. Yeah, I will come back to it later. Now I define a couple of constants. As I said, the constant C2 we have already seen in the definition of the set UC. As I said, it is 8. In the paper, I'm using the constant C2 because as I wrote the paper at the beginning, I didn't knew what the value of the constant is. I just knew there will be a constant. So throughout the paper, I'm using the constant C2 and C1. And then on the beginning, I defined what the value is. And then I define this function lambda with 2 parameters. For the meaning, I will comment later. For the moment, just consider just remember that there is some function lambda with 2 parameters. Then I define, maybe I will explain this on the later. So I select, basically here I select some minimal value for the h. The meaning of the h will be, as it was presented a couple of minutes ago, it will be the number of the non-periodic palindromic prefixes. So here I derive the minimal value of the h. This is the h0, such that my result apply. So using this limit and this function, I derive the value for h0, and for every h which is bigger than h0, I will be able to prove the conjecture. So basically it says I will consider only factors that have more non-periodic palindromic prefixes than h0. Yeah. Also, I will show, this is simple. I will show that that in the infinite aperiodic word, there is, for arbitrarily h, there is a factor that has h non-periodic palindromic prefixes. For this, I use some other result that has already been presented in some other paper. If I have infinite aperiodic word such that the palindromic length of its factors is bounded, then there is an infinite suffix that has infinitely many palindromic prefixes. This is known already for a couple of years, and using this result, I derived that there is also a factor for any given h. There is a factor that has h non-periodic palindromic prefixes, and I select the factor z using this requirement that the h is bigger than h0. Now I define the set Vm. So it is the set Vm are the positions in the vector z that can be achieved, that can be that are equal to the length of the concatenation of m palindromes. So if I have m palindromes, I can concatenate them, and the length of this concatenation is in the set VM. So this is here. I came to as I explained the proof from the paper from 2013. I will show that using this set VM, I cannot cover all the base positions. So VM are the positions that can be covered by concatenation of M palindromes. As I said, I selected the factor Z in such a way that the number of non-periodic palindromic prefixes is equal to H, which is bigger than E0. Then I define again some function theta M. The meaning will be, I will clarify in next minutes. Yes, I will need the definition of the so-called xi cut. So if I have a set of integers, and if the set of these integers is not empty, then for the okay, sorry. Yeah, so I have a set of the integers, and then I consider some subset of this set. And if the difference between the maximal and the minimal value of this subset is smaller than xi, then I set that this set D is a xi cut of the set D with bar. Yeah, okay. I was sorry, forgot the exact meaning of these symbols here, but yeah, okay, now it is clear. So it is just for the set of integers, I consider some subsets of this set that such that the difference between max and min are smaller than some parameter xi. The xi represents the period, will represent the period, and the d will represent some set of positions. So I mean this with the xi cut, this will be the positions from one period of a given factor. This will be the meaning of the xi cut. So now I define the NPS. The abbreviation NPS stand for nested periodic structure. So I start with the nested periodic structure with the tilde over. So it's a set of couples. The first parameter in the couple is as I said, D is some set of the positions, and the xi is the period, because the set of positions represents some factor of the word Z. Given the minimal position, given the minimal value of D and the maximal value of D, I have starting and ending position of the word Z, and this defines a factor of the word Z. And then I claim in this definition that this factor is periodic with xi. And then here I define also the spread and the close. Okay, I didn't state the definition explicitly. I will skip it. I think for this presentation, it's not crucial. If I need, I will come back to it later. For the moment, you can just remember NPS with tilde is the set of couples, let's say, of periodic factors, and every that are periodic with the period xi. This is for the moment, I think, sufficient. Now, what I need. No, I will come to it later. Yes, now I define nested periodic structure. I will explain it easier than the definitions are. So I define recursively, I define the nested periodic structure. For the parameter 0, the nested periodic structures are just positions of the word Z. You see, I define that these are the couples from the NPS with tilde, and I claim that the size of the set D is 1. It means in every set D there is only one position. So it is clear that one position is periodic with every period. So finally, in the set NPS 0, you can imagine there are all the positions. One element, one position in the NPS 0. For the parameter bigger than 0, I defined these are the vectors that are periodic with Xi, and every period of this vector is at most is a union of at most theta m nested periodic structures of lower degree. This is what the definition says. The attribute with the clause, for the moment, you can forget about it. So for the first level, for the level 0, I define these are just positions, single positions. For the higher degrees, these are the periodic vectors, and every period is a union of at most theta m of nested periodic structures of lower degree. So this is what the definition says. So you can imagine you have some periodic vectors, and then you compose them together, or you have some periodic vector, and in every period of this vector there are some other periodic vectors of lower degree, and the number of them is bounded by theta m, and so on. So this is the definition of the nested periodic structure. So this is something like, yeah, it's periodic, but every part is a periodic vector, and every part of it, every small part, every single period contains some nested periodic structures of lower degree. So this is the idea. Okay, this is what I explained. Yeah, the couple D, Xi, for this presentation, consider it as a vector, as a periodic vector. And now the second most important result of the paper is this one. A couple of slides before, I defined this set Vm as the positions that can be reached by the concatenation of m palindromes. And I show that all the positions that can be achieved by the concatenation of m periodic palindromes are a subset of some bounded number of nested periodic structures of degree m. So I have some bounded number. The bound is here. It is the constant C3 multiplied by h powered to m. This is the bound for the number of nested periodic structures. So I have some bounded number of nested periodic structures, and the positions that I can achieve using concatenation of m palindromes are a subset of this of the union of these nested periodic structures, if we consider nested periodic structure as sets of positions. This is in the big union here that I make the union over the set D over the set of positions. So this is the second important result. I think it's not that crucial. I will show you the idea of the proof, or I think it's not that complicated. I will, on the next slide, I will show you the idea. And it looks like this. So, excuse me. On this picture, I have there is some in the left down in the left corner down there is some black point. This is, let's say, this is one position. So I will explain the proof for the one single position. And in this single position, I have some given number of non-periodic palindromic prefixes. In this case, 3 on this picture. And for every, these are distinguished by the different size of the half circles. So the smallest half circle is the shortest palindromic prefix, 1. And then every non-periodic palindromic prefix has some periods. So you can notice that some of these, the smallest one and the biggest one, have some repetitions. For the second one, in the picture, I suppose there is no periodic extension of this palindromic prefix. The first have some and the biggest one have also one. And now the idea is that for given palindromic prefix, if we pick one of these 3 non-periodic palindromic prefixes, for example, the biggest one, every non-periodic palindromic prefix allows me to construct one nested periodic structure. It means using this palindrome, I repeat the point on the beginning, I repeat it, I mirror it using the palindrome to some next position, and again and again. There can be arbitrarily many repetitions of the palindrome, and this is the idea. And so I construct one nested periodic structure. So using one single point, in this case, I construct, because there are 3 non-periodic palindromic prefixes, I construct 3 nested periodic structures. So I say, using one palindrome, I can, all the positions that I can achieve using one palindrome, all these positions can be covered by 3 nested periodic structures. And so on. Of course, if I have, instead of one position, if I have a bunch of positions, it gets more complicated. I have to split it into nested periodic structures, and then, but the idea is the same. Using in every point, I have at most H non-periodic palindromic prefixes, and every single one allows me to construct another nested periodic structure of higher degree. So somehow intuitively, if you think about it, I think you would agree with me that the bound for the number of nested periodic structures is polynomial in the H. If H is the number of non-periodic palindromic prefixes, the number of nested periodic structures that I need to cover all the positions that I can achieve using concatenation of M palindromes is bounded polynomially with the regard to H. So yeah, in the paper there is the exact derivation of this formula, but just to see that it is polynomial, I think it's not that difficult. Yeah, and actually that's it. Yeah, these 2 results are the base, are the most important results of the paper. If I put them together, I have the result. So here I say I have polynomially many, let's say, nested periodic structures. And if I have one nested periodic structure, it can have many periods. But as I shown before, for the base positions that I want to cover, only a small number of periods are of relevance. So we can say that I can cover only polynomially many base positions. But we have seen that the number of base positions grows exponentially with age, because it is this structure of binary tree, and the number of the leaves in the binary tree grows exponentially with the number of levels in the tree. So this is, yeah, that's it. Then with these two results, it's just a simple exercise to prove the conjecture. Here, yeah, I will stop here. I think there is no more slide. Yeah, finished for the moment. Back to
All right. Thank you. Thank you very much.
Thank you too.
So we'll take some questions. Hajime.
So thank you for nice results. And may I see your main results again? Maybe page 3.
You mean the conjecture?
Yeah, yes, conjecture.
Okay. So the conjecture, as it was stated, this is the conjecture from 2000.
Yes.
And here's the paper. Yeah.
Yes, my question is, in the case where X is a Sturmian word, for example, is it possible to estimate PLU in terms of the length of U? If X is Sturmian.
Okay, no, I'm sorry. I think Sturmian words are not my strong side. So for me, it's difficult to say. No. Now, when I should think of it for a couple of seconds, I am not able to give you an answer. No,
sorry, I can answer. I can answer. I have a paper on that. And sometimes yes, and sometimes no, because it depends on the continued fraction expansion, if it is bounded or not.
For example, Fibonacci words is possible?
Well, no, in fact, because for the yes, you're right. It's more complicated. For the problem is that in the case when it is when the continued fraction expansions are bounded, when the terms are bounded, like for example for the Fibonacci word, we only have a probabilistic proof of the same kind that here that there is only a polynomial number of positions which can be covered, and we have an exponential length, something like that. And so there is no direct bound, but yes, I think it can be derived. Yes, there is yes, we can derive a bound from that, even though we didn't do it. But for some other Sturmian words, when, for example, the continued fraction expansions are more complicated, the bound is not so uniform. It will be. I also think we can derive it, but it will be nasty. Sorry, I also need to think about it. I never asked this question.
Thank you. Thank you for your answer.
Yeah, thank you too.
Does anyone else have any questions?
Well, I have not a question, but a comment that it's great. Well, in the beginning, Josef said that it is not too much technical, and we all saw that it is was not the case. It is technical, and it was too technical for me all this time, because if I could, I would prove it in somehow similar technique, but I never was able to do it, because the combinatorial construction was just too complicated for me. I could imagine how how it should look like, but I never managed to do all the technical details. So I am very, very impressed.
Thank you. Yeah, I see. I agree. I think there are a lot of definitions. I would say I already talked to Narat before this presentation. Yeah, I would say every single definition, every single proof. I think I would say it's not difficult. Probably it's the number of cases that must be considered separately. Yeah, I will try for the next versions. I will try to include some more images, more explications. Yeah.
It is very bulky construction, indeed.
Yeah. But for me, I would ask maybe the essential result that I called with the base positions was this comprehensible? This I think just this one, that the base positions are from the set UC, means that if I try to cover the base positions with the periodic factor, I can consider only a small number of periods. Was this part at least somehow clear?
Well, I understood the main idea, but I must say that it is very technical, and I'm really sorry that in these months I did not have the time to really read your paper in all the details. But yes, I see this construction, and because I was thinking about something similar and never had enough memory to manage it.
Okay, but thank you for the feedback. I see it will need some more time to make the paper readable. Okay. But anyway, we have the direction, we have the ideas.
Svetlana, do you have a question?
Yes. Can you hear me?
Yes.
Yeah. So thank you very much for the nice talk. I have a general question. Well, it's super technical, as Anna said. And instead of factorization into palindromes, one can consider factorization into factors of some other form, like privileged words or powers, or you can require that in a word certain letters are equal or something like that. And then you can ask the same question. So if you consider factorizations into factors of a certain form, and if each factor can be factorized with only finitely many factors of this type, does it follow that the word is periodic? So do you think your technique could be generalized for other types of regularities, or is it really very much specific to palindromes?
Okay, I was frankly, I was not thinking about it. I think some generalization would be possible. I think at least the privileged words, I would say it would be possible for general powers or for powers. I'm not sure. I will take it with me. I will think of it.
Yeah, because for privileged words, or if you consider factorizations into, say, squares or squares and cubes to avoid problems with odd lengths, then you also, with the same counting argument, you can see that you have unbounded exponents in your word. So maybe.
Yeah, as also I now maybe at least I understand the question, but I have to say the same like a couple of minutes before. Now, when I think of it for a couple of seconds, I'm not able to give you any good answer. I need some time, but it's a good inspiration for some next research.
Thank you.
Yeah, you're welcome.
Thanks. Does anyone else have a question? If not, thank you again, Josef,
Thank you too.
for explaining your really nice result. And thank you to all of you for coming to the talk today. And hopefully we will see you all again in 2 weeks for our next seminar.